Just froze. All right. So in section 9, we're going to talk about the derivatives of exponential functions and logarithmic functions, right? So first of all, let's take a look at e to the x, right? The derivative of e to the x. That's like one of my favorite functions to take a derivative of. So take a look at what happens. So do you remember when we first learned about derivatives, we did it using the definition, right? You remember that definition? So it was the limit, so f prime of x is the limit as h approaches 0, f of x plus h minus f of x over h. So now, if f of x is equal to e to the x, then f of x plus h is e to the x plus h minus e to the x, okay, over h. So now, let's think about this for a minute. If I have 3 to the 3 times 3 to the 5, what is that? 3 to the 8, right? You add these, right? So now if I have 3 to the 2 times 3 to the x, how much is that? 3 to the 2 plus x. Now, suppose I have this and I want it to go backwards. So if I gave you 3 to the 2 plus x, can I go backwards and say that's 3 to the 2 times 3 to the x? I can say that, right? Because what happens if I add these up? I get 2 plus x. So coming back here, I have e to the x plus h. Well, guess what? I can separate that into e to the x times e to the h. Do you see how this is the same as the circle thing on top? Yeah. Right? So now I have e to the x times e to the h minus e to the x. Okay, let's factor out an e to the x. That'll be the limit as h approaches 0, e to the x, e to the h minus 1 over h. Okay? Now, if it's e to the x times something, can I write it off to the side here? Yeah. E to the x times the whole thing? Yeah? Okay, now let's put in an h. H is 0, right? When h is 0, we don't put anything in here. But here when h is 0, what does that turn into? 1 minus 1? 0, right? So what happens?
0 over h.
Right. Okay. So this though, okay, e to the h minus 1, that turns into a 1. We'll talk about why later. Okay. And so now you have that the derivative is just what? E to the x. Okay. So the moral of the story is the derivative of e to the x is just e to the x. Okay? Yeah. I know. So you will never have to do that. But you will just have to know this. The derivative of the e to the x is just e to the x. Yeah.
Do you need to know why that's?
No. Okay. And now, if the derivative of e to the x is e to the x, right? Then if it's e to the u, then we do the chain rule. So it'll be e to the u times du dx. Okay? That means e to the whatever times the derivative of this. So let's do one here. Let's find dy dx. Okay, so here we have not e to the x, but e to the 3x. So this is u. So dy dx is going to be e to the u times the derivative of u, which is 3. Okay, so that's just 3e to the 3x. Okay? Huh? Yeah. All right. So let's do this one. Here, this is u, right? So dy dx is e to the x plus x squared times, right, 1 plus 2x. Now, normally we write the algebraic functions before the exponential functions. So this will be 1 plus 2x e to the x plus x squared. So in taking a derivative of exponential functions, the exponential function as is will always show up in the derivative as is, okay? All right, now, the derivative of ln of x. So the derivative of ln of x has a similar situation. I'm not going to go over it, right? But basically, how are e to the x and ln of x related to each other? What's e to the x compared to ln of x? One is the inverse of the other, all right? So we find the derivative the same way as we find the, the derivative of inverses. But I'm not going to make you guys go through it. Basically, if you go down to the box, d dx, the derivative of ln of x is 1 over x. I know it's like straight out of left field, but it's similar, just like this, inverse sine derivatives. It is what it is, okay? So the derivative of ln of x is 1 over x. And then if u is a differentiable function, then it's 1 over u du dx, meaning you have to apply the chain rule where appropriate, okay? All right, so here, y equals ln of x cubed. You have to take a derivative. So y prime is, the derivative of ln is 1 over. So immediately I do 1 over x cubed times the derivative of u, 3x squared. And so now you have to simplify, of course. So the x squares cancel with the x cubed on the bottom. So y prime is 3 over x. All right. There's supposed to be a set of parentheses here. So this is ln of 10 over x, right? And I purposely leave them in that form because I want you to recognize that that could just be rewritten as ln of 10 over x. All right? Yeah. Here. Right, and then further, this will be ln of 10x to the minus 1. I like to write it like that. Okay? All right, so now, y prime, ln of blah, the derivative will be 1 over the blah, right? So 1 over 10x to the minus 1 times the derivative of this. So this goes down, so it's negative 10x to the minus 2. Okay? Oh my God, I'm so sorry. 1 over 10x to the minus 2. And now, what? You can cancel out the 10s. So this is negative x to the minus 2 over x to the minus 1, right? So it's negative x to the minus 1, right? Because you do negative 2 minus negative 1, negative 2 plus 1, so it's minus 1. So that's negative 1 over x. So dy dx is negative 1 over x. Okay? All right. So power rule for arbitrary real powers, right? We're still working with these powers. So if u is a positive differentiable function of x and n is any real number, u to the n is a differentiable function of x. And, basically the same situation. When you have a power, it comes down, and then you take a derivative, and so on. So if, for example, you have to find d dx of 10x to the 6, what would that look like? 60x to the 5. Okay? All right, so what happens here? Okay, here we have a square root of 2 as an exponent. Okay, it's not an integer. Fine, you can still subtract the 1 from it, right? So dy dx here, right? The root 2 will come down. So it's root 2 x root 2 minus 1. That's it. That's it. Don't go and do like 0.41 whatever. Don't do that. Just leave it as root 2 minus 1. I would rather that than anything else. Okay? Yeah.
What was it saying up here then? Does anything up there have to do with what we just did?
Absolutely. Because if u is a positive differentiable function and n is any real number, so look at the root 2 here. Is that a real number? Right? So no matter what the exponent is, if the exponent is a real number, then you still bring it down and subtract 1. Right. So here, the pi is going to come down. Now, this is a chain rule function, right? I mean, it's one where there is a chain rule. So dy dx is pi times 2 plus sine 3x to the power of how much? Pi minus 1. Again, it's not 2.14. Okay, it's pi minus 1 times the derivative of the inside, which is cosine, just that, times 3. Yeah. Cosine 3x times 3. Okay? So this is 3 pi cosine 3x times 2 plus sine 3x to the pi minus 1. All right? We always like to write the like the algebraic function, non-exponential, non-trig functions before. And then, we sort of like go like complex to more. But that's not as important as, always bring the algebraic functions to the front. Okay? All right. Okay. Logarithmic differentiation. Here we go. Here it is. You ready? Here it is. Okay. It's so much fun. Okay. Okay. When do we use logarithmic differentiation? I'll tell you when we use it, and then we'll talk about what it is. Okay. Basically, when you have a function in which the variable is involved in the base of the exponent, in the base and the exponent. So for example, most of the time we have, these cute little boring functions like x to the 3 or, sine of x squared and so on. But what if you have x to the x? Then what? Right? Oh my word. So does that qualify? Is the variable involved in the base and the exponent? Yeah. Yes, it is. Okay, so then what do? Do we just close the book and go home? No. Logarithmic differentiation is what we do. And you know what? Go and throw that word around, like I'm doing logarithmic differentiation and see, right? And see what kind of parties you're invited to then. Okay. So how does this work? How does this work? Basically, first, you take the ln or log of both sides, right? So take a look. If you took the ln of both sides here, right? Then you have ln of y equals ln of y equals ln of x to the x. Do you remember properties of logarithms where if you have ln of something to the power of something, what happens? This moves down and then it's less of a scary function. That's the reason why we do it. Okay? So, and then you do step 2, use the power rule to move the exponent to the front. Then everybody's favorite, implicit differentiation, to differentiate both sides. Solve for dy dx. Replace y with what y was equal to in the beginning, and then we're good to go. Okay, so let's just do it. Okay? All right. Step 1. Okay, so here we go. This is the one I was just talking about, right? X to the x. Everybody's favorite function. Okay?
How do you know when to do log or ln?
We always do ln. We're going to do ln mostly. Okay, so let me write it here. So y equals x to the x. We're going to take ln of both sides. And now this x comes down. So I have ln of y equals x ln of x. Okay? We just did step 2. All right? Now, okay. Next, what's the next step? Implicit differentiation. Implicit differentiation means take a derivative of both sides, and that's when we have dy dx show up, right? Okay. So, what's the derivative of ln? 1 over, right? So here it's going to be 1 over y dy dx, right? So this is my implicit differentiation. Okay? And now here, what are we going to do? Product rule. So u equals x, v equals ln of x, u prime, v prime. All right? Next. So here we're going to do uv prime, so x times 1 over x plus ln of x. So now I have 1 over y dy dx is equal to 1 plus ln of x. Okay, so we are here. We just did step 3. Step 4 is solve for y, solve for dy dx. To solve for dy dx, I'm going to multiply both sides here by y. So dy dx is 1 plus ln of x times y. But now, I can't have y show up as a variable in my function, in my derivative. So that takes me to step 5, by which time I had lost you when I was doing the steps, but now you know, it's relevant now. Replace y with what y was equal to in the beginning. Right. So dy dx is equal to 1 plus ln of x times x to the x. Right, and then to write it in cleaner form, we're going to say x to the x, 1 plus ln of x. Okay? Now, let's have a little fun with this stuff, all right? I know by the time we get here, we forget some of these things. So, if I have ln of x squared, another way of writing that is negative 2 ln of x. We know this, yes? Because, I'm sorry, not negative 2, positive 2 ln of x. Because the 2 comes down. Okay? So if I have ln of 1 over x, look at the different ways of writing this. Ln of 1 over x is ln of x to the minus 1, right? And then when the negative 1 comes down, this is the same as negative ln of x, right? So often in the book, or let's say it's a multiple choice question, you know, the answer, you might find the answer in this form, it'll show up in this form, and vice versa. So a good calculus student, a sophisticated calculus student, will have no problem going back and forth between ln of 1 over x, negative ln of x. Another very, 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 very common thing is this, ln of 1 over 4. Okay? This is, okay, so when we're dealing with ln's, we always want these numbers to be simplified into the most elemental base. So if you take 4, what's the most elemental base from which 4 comes? 2. So I can write this as ln of 1 over 2 squared. Is that right? Not 2 times 2, because ln is the inverse of an exponential function. So it's all about bases and exponents. So now, is that the same as ln of 2 to the minus 2? So is that the same as, I'll write it here, negative 2 ln of 2? Yeah? Often in the book, often your answer will be ln of 1 over 4. The answer in the back of the book will be negative 2 ln of 2. And you have no idea how many times a student will come to me and say, I'm not getting the same answer as in the book, they're getting this, I'm getting that. But they're the same. Okay? So always see, you know, and like this is my favorite thing, right? So always see how you could rewrite those. Yeah.
Can be rewritten as negative 2 ln of 4?
No.
Negative 4.
No. This is it.
Okay.
Okay? All right. So just letting you know. Okay, all right. Ooh, look at this one. X to the power of sine of x. Never in your wildest dreams did you ever imagine you would ever come across a function like this.
No, I did not.
Right? Okay. So here is one. How do you know to use logarithmic differentiation? You've got an exponential function. You've got x in the base. You've got x in the exponent. That's perfect for logarithmic. So I take ln of both sides. This comes down. So I have ln of y equals sine x ln of x. Now what? Well, first it's what kind of rule? Product rule. So u is going to equal sine x v ln of x. So u prime cosine x. Imagine if that was like sine of 4x or something, right? Then you would have had to do a chain rule. V prime 1 over x. So when we do implicit, this is going to be 1 over y dy dx. Here, what are we going to get? Right, 1 over x sine x, right? I always do my algebraic function first, plus cosine x ln of x. Okay, can I simplify anything here? No, not really. Times what? Times y, and then replace. So you see, it's not that scary. dy dx is equal to 1 over x sine x plus ln of x cosine x times, what's y? No, the limit as h approach, yeah. So we rewrite that as, yeah, x to the sine x, parentheses. And now this, why don't I just sine x over x? Look at you guys. Perfect. Perfect.
Does it matter about the last one?
No, ln and cosine, no. All right? You see that? Okay, so not as scary as we think. Okay? It would have been, so The implicit differentiation we did before, right, where you had to do like the second derivative, that's a bit scarier, I think. Now, see, you guys are becoming like these mature, like sophisticated, math students where nothing phases you anymore, right? Okay. I'm gonna take out number 29, okay? But the rest you're doing.